Praise be to God, and peace and blessings be upon the messenger of God, Muhammad, and upon his family and companions. Now as for what follows, by time, mankind is in loss, except those who believed, did righteous deeds, and advised truth and patience. In the first episode, we explained the general operation principle. Before details, we explained relay development history and how technology evolved from electromechanical to static, digital, and numeric relays. Stay with us. Relays became smaller and more reliable. Our course focuses on relays and how technology has evolved from electromechanical to static, digital, and numeric relays. As technology advanced, relays became smaller and more reliable with modern techniques. This course focuses on relays, but will also cover other types still used in older stations. Relays are now smaller and more reliable due to modern techniques. The first generation, electromagnetic or electromechanical relays, dates back 100 years. Mechanical relays, though limited, are the foundation of modern relays. Protective relay is the American term, while protection relay is used in Europe. The remarkable renaissance of a nation. The first generation is the electromagnetic or electromechanical relay, which dates back about 100 years. Mechanical relays are considered the simplest forms of protective relays. Although their functions are very limited, they represent the foundation for all modern relays today. It's important to note that the term protective relay is used for relays according to the American standard, while the European standard refers to them as protection relays. The inventors of electromechanical relays are considered true geniuses because they managed to apply their knowledge of electrical protection systems to create relays that mimic the desired characteristics or achieve the goals they aimed for, using the principle of electromagnetism and its mechanical effects. Their operation is based on exploiting the property that the current passing through a coil generates a magnetic field associated with it. A magnetic force affects a disk, causing it to spin at a speed corresponding to the current intensity. The disk rotates when the current exceeds a threshold and spins faster as the current increases. This is used in induction disk relays. Trip time is set by adjusting the disk's rotation distance to close the output contact. The longer the disk travels, the longer it takes to close the contact. This video demonstrates testing this relay by injecting current at points 9 and 10. As an injection device, how do I know if the relay has issued a trip? Adjust trip time by setting disk rotation distance to close output contact. Select time delay control position. Trip time ranges from fractions of a second to 30 seconds. Longer disk travel means longer to close contact. We demonstrate relay testing by injecting current at points 9 and 10, simulating CT current. To know if the relay trips and calculate timing, take feedback from output contact 1 and 2, connect to injection device. If contact closes, relay has tripped. Set current value for relay operation. We will demonstrate how to test this type of relay by injecting current using an injection device at entry side, which are points 9 and 10, simulating current from the CT. How to know if relay tripped. How to time this decision for tripping time. Connect output contact 1 and 2 to injection device. If contact closes, relay tripped. Set relay current by pin in slot. Insert to 0.75 for 0.75 amps. Choose TMS by dial. Select 0.4 for line. Connect output contact 1 and 2 to injection device. If contact closes, relay tripped. Set the current value at which the relay should start operating. Insert the pin into the slot at 0.75 to set the current to 0.75 amps. Rotate the black dial to select the TMS value, here 0.4. Older relays have limited curve options, unlike digital relays. Connect the relay's output to the injection device's binary input to calculate trip time. Connect the current output from the device to the relay and inject 1.4 amps, exceeding the 0.75 setting. Select values from 0.1 to 1. Older relays have fewer curve options than digital ones, which select one curve like normal inverse, over inverse, or extreme inverse. Connect the relay's output to the injection device's input to calculate trip time. Connect the current output from the device to the relay and inject 1.4 amps, above the 0.75 setting. Using previous course equations, predict trip time, ensure accuracy, and calculate error. Once injection starts, the timer runs until the output contact closes. Notice the disk rotates because the injected current exceeds the setting. This indicates that the relay has issued a trip before, and it can be reset by lifting it up by hand. Now, we connect the output contact of the relay to the binary input of the injection device so it can calculate the trip time. Then, we connect the current output from the injection device to the relay and inject a value of 1.4 amps, which is higher than the setting value of 0.75 amps. Using the time calculation equations mentioned in detail in the previous overcurrent course, I can predict the trip time, ensure it's correct, and calculate the error percentage. Once we start injecting, the timer begins to work and won't stop until it receives a signal that the output contact has closed. Notice how the disk rotates because the injected current value is higher than the setting value. The disk continues to rotate until the contact closes, and once the contact closes, this flag appears. Here we notice that the tripping time is 24.7 seconds, and we calculate the expected time using the curve used or the equations to ensure that it is correct. We explain the operation of the induction disk relay. 1. Current flows through the feeder via primary CT. 2. CT converts high current to 1 or 5 amps, then sends it to the induction coil. 3. Current in the induction coil creates a magnetic field. 4. This magnetic field intersecting the iron core generates magnetic flux. 5. Magnetic flux flows through the iron core, divided into left and right poles, distributing the main flux. Main flux is left plus right flux, as shown. 6. Dividing flux creates torque from their interaction. This magnetic flux flows through the iron core, which is divided into left and right poles, and the main flux is distributed between them. Thus, the main flux is the left flux, plus the right flux, as shown in the image. The purpose of dividing the single flux into two fluxes is that we want to create a torque resulting from their interaction or intersection with each other. We install a component that we place on one side of the riscs and not the other, so that it helps the magnetic flux change its angle. The two magnetic fluxes should not remain identical. The rotating disk must be electrically conductive to allow the current to flow through it. We install this to slow down the rotation of the disk or to prevent the disk from rotating incorrectly when current flows through it. The 10th and final point is that once the disk closes, it must be manually reset as long as there is no spring to return it to its normal position. This is the function of the helical spring. The 10th and final point is that once the disk closes, it must be manually reset as long as there is no spring to return it to its normal position. This is the function of the helical spring. The spiral and the spring. If we use this, the torque of the disk will arise from the interaction of the current flux with the voltage flux. These devices are characterized by being always stable and not affected by the vibrations that may occur in the electrical network. Additionally, engineers have extensive experience in dealing with these devices over the years. However, a drawback is that they have a relatively slow response due to the inertia in the moving parts, as they need some time to start moving. Additionally, they require regular maintenance and need calibration from time to time to ensure measurement accuracy. This relay is a high burden for CT and VT. We use a resistor car. Pilot transformers connect to mechanical relays, with each phase having one stage. Thus, 3 relays are needed for overcurrent protection, 50, 51, and another for earth volt protection. This setup allows removing any single-phase relay for testing or maintenance without affecting the system. A trapping circuit with all output contacts in parallel ensures that if any closes, it activates the lookout relay, 86, and trips the circuit breaker. How the pilot transformers connect to the mechanical relays. Each phase has a mechanical stage. Thus, we need 3 relays for 3-phase overcurrent protection, like 50, 51, plus another for earth volt protection. We can remove any single-phase relay for testing without affecting the system. The image shows a trapping circuit where all output contacts are connected in parallel. So if any close, it activates the 86 relay, tripping the breaker. This means that we can remove any single-phase relay for testing or maintenance without affecting the entire protection system. This image represents a trapping circuit showing that all output contacts are connected in parallel. So, if any one of them closes, it will activate the lookout relay, which is 86, and in turn, it will trip the circuit breaker, which in turn will disconnect the breaker wire. We were tasked with upgrading the power system by replacing old electromechanical relays with modern numeric ones. We modified the CT and trapping circuits, adding new CTs for line differential protection on the 34.5 kV line. Changes are marked in the cloud shape. The image shows the modified trapping circuit with modern relay contacts. The second generation, static or solid-state relays, emerged in the early 60s with no moving parts, reducing operational errors. The modifications are marked within the cloud shape, and you can follow them and compare the changes that occurred if you want to delve deeper into this topic. This image represents the previous trapping circuit, but after making the modifications, removing the output contacts coming from the old mechanical relays and replacing them with output contacts coming from the modern mechanical relays. The second generation is the static relays, which rely on electronic devices without moving parts. They use operational amplifiers to compare circuit current with a set current. Analog inputs are converted to small voltages. These relays are smaller, lighter, and consume less power. Its design uses electronics, not coils. Older versions had transistors, diodes, capacitors, and resistors. With electronics advancing, integrated circuits became usable. Static relays work by comparing circuit current with a set current. All analog inputs are converted to small voltages. This relay is smaller, lighter, and consumes less power, lowering CT and VT burden. It has a long lifespan due to no moving parts. However, it's sensitive to temperature changes and voltage spikes can damage it. Inputs convert to small voltages. This relay is compact, lightweight, and low power. Long lifespan due to no moving parts. Low temps affect operation. Voltage spikes and resonance cause false operations. Thus, unstable and short-lived in service. Its formulation is minimal, contributing to its long lifespan and unaffected by operations. However, it is sensitive to temperature changes, operating at low temperatures. Additionally, voltage spikes can damage the relay. Static charges can damage components if not grounded. Thus, this relay is unstable and short-lived. Current and trip time are adjusted by moving switches, depending on relay type and setting. Assume final setting is very inverse with TMS 0.2 and setting 1.2a. Adjust current by moving switches. Assume final setting, very inverse. TMS 0.2, 1.2a. Upper area is for inverse protection, lower area for instantaneous overcurrent. To select very inverse current, choose 1, 0, 0. Move first switch right, second and third switches to 0 on left. Notice with me that the upper area is for inverse type protection, as shown by the shape of the drawn curve, while the lower area is for instantaneous overcurrent. Now, to select the very inverse current, this table tells me to choose 1, 0, and 0, which means we move the first switch to the right using a regular tool, and we move the second and third switches to the 0 position on the left. As for the setting being 1.2 amperes, it results from the sum of 0.8 amperes plus 0.4 amperes. Therefore, I move this switch to the left towards 0.4 and 0.8. As for the TMS being 0.2, we move the switch next to 0.2 to the right. It is customary for the table and the settings to be drawn on the relay itself, so we may not need the manual in this case. We explained the testing method in detail in the previous course, and this is the connection specific to this relay in case you need it. As for static differential protection, one of its types is the NBCH12 relay, which is now extinct and no longer exists. The following image represents a block diagram of a biased protection relay of the NBCH12 type with two biased inputs. NBCH12 with two biased inputs. MC12A static release, set over current. Now we want to explain to you how to set up and test the static release. We want to test the static release of type MC12A. The overcurrent setting is 2.4 amps and it trips after 10 seconds using the definite time curves. The equation given on the relay is equal to 0.1 R plus R multiplied by the sum of A and all multiplied by IN. The value of capital R here depends on the current real selection used. 10%, 40%, 1, 20%, 50%, 2, 50%, 200%, 3 man, percent, 40%, switch off on off. For 50% to 200%, choose 3. For 10% to 40% usage, switch. Off on off, repeat. Off is down, on is up. Replace R with 1. In is current from CT. Assumed 1 amp. To set I to 0.4, I, jar 0.1, R plus R, sum A, all, IN. Here, I, jar 0.1 plus sum A, jar 0.4, so sum A, jar 0.3. Choose A via switches. 0.16 plus 0.08 plus 0.04 plus 0.02, verify 0.3. To set I to 0.4, use the equation. I setting I have 0.1, R plus sum of A, IN. Here, I setting I have 0.1, 1 plus 1, IN, R is 1. So I setting I have 0.1 plus sum of A, I have 0.4, making sum of A, I have 0.3. Choose the values through switches to get 0.3, 0.16, plus 0.08, plus 0.04, plus 0.02, I have 0.3. Move these switches right to achieve 0.3. After setting I, set time to 10 seconds by adjusting the trip time characteristic factor K with the definite time switches. 0.3 is 0.6 plus 0.08 plus 0.04 plus 0.2 and is 0.3. Move switches right for 0.3, set I, then time to tens. Adjust trip time characteristic K by setting switches to on, off, on, off, on, up, off, down. Set time using trip time plus K, 0.1 plus T. K path tens, output tens, multiply by 1, theta 0.9, which is 0.1 plus 0.8. K is 10 seconds, and the output should match, so multiply by 1. T equals 0.9, which is 0.1 plus 0.8. Move switches 1 and 4 right, leave 2 and 3 left. Use. It's a sum. So we move the switches for these two numbers, which are 1 and 4, to the right, and we leave the others, 2 and 3, to the left. Using the same previous connection, we provide current and take the output contacts. We connect the wires to points 5 and 6, which are the normal open contacts coming from the relay. Then we inject current into points 11 and 12. Here, there's a very important point that is not present in the electromechanical relays. This relay requires a supply to function, either AC or DC. Connect the supply, points 2 and 3, and ground point 1 to prevent static charge. Inject a current above the setting, here 0.4 amps, 0.45 amps. The relay should trip after 10 seconds. It tripped at 9.87 seconds. Calculate the error percentage from 10 seconds to determine test success. Point number 1 is for grounding to avoid any static charge during the test. Now we inject a current value higher than the setting current, which here is 0.4 amps. Let's say the value we want to inject is 0.45 amps. The relay is supposed to issue a trip signal after 10 seconds. We notice that the relay tripped after a time of 9.87 seconds. Then we calculate the error percentage from 10 seconds, and based on the technical data sheet for this relay, we determine whether the test was successful or not. The third generation of relays, digital, emerged in the early 1970s. They convert signals into digital numbers stored in memory, updated every millisecond. Only 1 or 2 cycles are kept in RAM, replacing old values. Digital relays use microprocessors, unlike older analog circuits. Limited microprocessor capabilities reduce sampling, affecting speed, thus limiting use. The fourth generation appeared in the 1990s. Of course, it's impossible to store every current and voltage value. Instead, 1 or 2 cycles are stored in RAM. Whenever a new value comes in, the largest stored value is deleted, and so on. In the digital release, microprocessors and microcontrollers were used instead of the analog circuits that were used in the old static releases. Due to the limited capabilities of the microprocessor used inside, the number of samples taken from the waveform of the current and voltages became low, which limits the speed of operation of these relays in some applications. This led to the digital release being used only in specific applications and protections. The number of samples taken from the waveform of the current and voltages has become low, which limits the speed of operation of these relays in some applications. This led to the digital release being used only in specific applications and protections. The fourth generation of these relays appeared in the 1990s. These are called numerical relays, which emerged as a result of the development of digital relays alongside technological advancements. This type of relay has the capability to use multiple digital signaling processors or microprocessors that are smaller and faster, all operating simultaneously, and improved to provide real-time signaling processors. In addition to its ability to distinguish fault currents from other natural currents that have the same value using what are called mathematical algorithms. After this development, the producing companies began to integrate many protective devices into one unit, relying on the philosophy of an all-in-one box, which is based on the fact that the hardware for all these relays is almost similar, and the difference between them lies in the software stored inside. This type of relay is now referred to as a multifunctional device. Of course, it is important to note that there are many issues with this technology, the most significant being that the failure of this multifunctional device could lead to a disaster due to the complete absence of a protection system. In the past, if one device failed, the other devices that were still operational would continue to function. This observation did not escape the designer's minds. So they provided him with backup protections, and it's often from a different company. It's preferable for each device to have its own separate DC source, and they should not share the same source. Some took advantage of the presence of old protection devices in the station and used them as backup protections. Here, the company benefits twice. Once by leveraging modern technology, which has many advantages, and again, by utilizing older devices that still work well. It's important to note that this type of relay is referred to as a numerical release according to the IEC standard, while the same type of relay is called a digital release according to the American IEE standard. This means that the European standard differentiates between the terms, meaning the European distinguished between the names. The term digital release was used for the old generation that utilized microprocessors instead of circuits, while the term memory release refers to the modern types that use modern computer type release. The American standard, on the other hand, used the term digital release for all types, both old and modern generations. Therefore, they refer to the modern types of relays as multifunction digital releases. This means that the terms numerical release and digital release are two words that, when combined, separate, and when separated, combine. This implies that if they are combined and I am asked to differentiate between them, there is definitely a difference in terms of size, response speed, ability to distinguish, and containing more than one function. And it will definitely be better. If they penetrate, one comes in one place and the other in another, there's no difference between them. So I can say that this is OR with the development, or digitally. And with development, it has the capability for protection, control, monitoring, measurement, and direct connection to communication networks. This has led to the emergence of a new term, Intelligent Electronic Device, IEDs, which is currently used in substations. In the past, we used to say differential relay or distance relay, but after the introduction of IEDs, which encompass all these protections, we now refer to it as distance function or differential function, not relay. Since a single IED contains all these protections, there's no longer a need to request a separate relay for each protection. This way, I have significantly reduced the number of relays. Recently, ABB released a new relay called REX 640, which is used to protect all areas of the power system. I can use the same relay and the same hardware for all protections, such as generator protection, transformer protection, bus bar protection, line protection, and others. This means all the features for the power system are now ready in one relay. However, this doesn't mean all features are ready. Each feature needs a license to use it without changing anything in the relay's hardware. Thus, you can remove a feature or add another as long as the points you have don't exceed the limit, no? Or you can buy new points from the maker. In the past, relays for generator safety were named generator relays. Relays for transformer safety were named transformer relays. Relays for line safety were named line relays, while relays for feeder safety were named feeder relays. However, this new relay has been named REX, with the letter X representing something variable, allowing you to swap it with the letter suitable for the safety, G, L, T, F, or others. As for this new ring, it was named BRICS, as if they meant here that the letter X is something variable, so that the letter you see fit can be replaced according to the protection, whether it is G, L, T, F, or something else. TFO. Other. This is the new trend among most manufacturers to make it easier and more flexible for the importer. The Ciprotec 5 Compact 7SX from Siemens operates on the same principle, and you can specify your requirements through an online interface. Inspirational. The National Awakening. What are the advantages of numerical differential protection? This modern protection is multifunctional regardless of the type of protection needed, and it has the ability to perform additional tasks like disturbance recording and measurement. This numerical relay performs self-monitoring comprehensively, meaning it has self-surveillance over itself. This means that if any problem occurs within it, it gives you an alarm with the number of that problem, and you can refer to the manual for this relay to understand the cause of the issue and the steps to resolve it. Alternatively, you can connect the device to a laptop and the internet to solve the problem remotely, which of course reduces the costs of routine maintenance. Well done! Digital measurement techniques and smart algorithms help detect inrush current and distinguish it from normal currents, maintaining system stability. Old relays required matching transformers for different transformer vector groups and city ratios. Numerical relays automate most calculations and offer internet monitoring. However, they are more complex and prone to misuse. In old relays, we needed to do matching transformers because of the difference in transformer vector groups by using different city ratio to achieve this goal. In numerical relays, most of these calculations are done automatically and online. Old relays lack this feature. They're complex, prone to misuse, and can alter logic easily. Many functions are hidden. Previously, drawings clarified connections, aiding problem solving. Now, relays are black boxes, with secretive operations and unhelpful manuals. Testing demands precision and organization. Hasty engineers may struggle. Meaning that you can add a letter, remove a letter, or add a space, and your logic changes completely. Many of the functions of the electrical protection system are not visible inside this type of relay. In the past, all connections were clear in the scatter drawings, and all information could be obtained in one place, and problems could be tracked and solved by tracing the wires. Recently, the relay has become a black box, and its working method is considered a secret that no one can see. Sometimes the information mentioned in the manual is general information and does not help in solving the problem. Testing these modern relays requires extreme accuracy, quick wit, and regularity in work. A hasty or disorganized engineer, or an engineer who does not read, usually does not succeed in such fields, because they will face many problems and won't be able to solve them. Best of luck to you all. We'll see you next time in the upcoming episode, where we will explain the principles of differential protection. Be sure to tune in.